We've been learning how to build and interpret linear regression models. Now it's important to step back and really question and evaluate our work. One of the most famous quotes in statistics states that all models are wrong. Mainly, just like model cars, architectural models, or Star Wars Lego models, statistical models are idealistic representations of more complex realities. That said, good statistical models can still be useful or inform our understanding of the world's complexities. To know whether our model is of the useful variety, there are three essential questions to ask. Is the model wrong? Or, perhaps more appropriately, how wrong is the model? Is the model strong? And is the model fair? In this video, we'll focus on the first of these questions. Is the model wrong? In general, a model is wrong when its assumed trend doesn't match reality. For example, using a sample of temperature data, suppose we built the following statistical model of Minnesota temperatures in degrees Fahrenheit by the day of the year. From the summary table, we thus estimate the following model trend, which we can interpret as follows. On average, temperatures increase by 0.045 degrees for every day of the year. If you pause long enough here, you'll recognize that this conclusion is a bit absurd. Mainly, the first clue that this model is wrong is simply context. Even before looking at any data, we know some things about Minnesota weather, and we shouldn't forget these things when it comes to our analysis. Whereas the model assumes that Minnesota temperatures increase linearly throughout the year, our experience reminds us that the relationship is more nonlinear. Temperatures start out cold at the beginning of the year. They then increase throughout the first half of the year. But they don't continue to increase and get warmer and warmer. Rather, they come back down again as fall and winter approach. We can complement this contextual understanding with visual evidence from the data. Just as we expected, the temperature data exhibit a non-linear trend. Thus, the linear trend, assumed by our model here, is simply wrong. It doesn't reflect reality. In this case, we can build a better model by assuming a quadratic trend in temperatures. This quadratic model trend, represented by the blue line, closely matches the nonlinear trend in our data. Thus, though this model isn't perfect by any means, it's certainly very reasonable. As you might expect, there's a catch here to relying on just context and the plots of our data alone. We'll soon study more complicated models that have two or more predictors, thus live in higher dimensions. Unfortunately, it's tough for humans to really wrap our minds beyond 3 dimensions. Mainly, we'll often find ourselves in the position of not being able to visualize our model. Thus, we can't check if our model is wrong using this approach. Instead, we'll utilize a visualization tool called a residual plot. First, consider one data point in our raw data plot. On this 183rd day of the year, we observed a temperature of 45 degrees. Yet we would have predicted a temperature of 64 degrees. Thus, the residual, or the prediction error, indicates that the temp we observed was 19 degrees below what we'd expect. In anticipation of the situations when we have too many predictors, x, and can't visualize our data and model as we've done at the left here, we can instead just examine the residual and prediction for each data point. So focusing on this pair of data points, or this pair of values for each data point. To this end, a residual plot plots the residuals on the y-axis versus the fitted values, or the predictions on the x-axis. Interpreting this plot requires more art than science, or simply a lot of experience. We'll get this experience throughout the semester. For now, let's just break down the residual plot here for our temperature model. First, notice that each dot corresponds to a single data point, or each dot in the residual plot corresponds to one of the raw data points. The dot highlighted here corresponds to the same raw data point highlighted at left. It's just drawn at a different set of coordinates. On that 183rd day of the year, recall that we predicted a temperature of 64 degrees. However, the observed temperature was 19 degrees below the prediction, or our residual for this case was roughly -19. Thus, every dot below this line of 0 represents a similar data point in which the observed temperature was below the prediction, or the dot or observation was below the trend. In contrast, each dot above 0 represents a data point in which the observed temperature was higher than predicted, or above the trend. In general, then, a residual plot converts the observed set of x and y values to the corresponding model prediction of y based on x, and the residual or difference between the observed y and this prediction. The next question is, why do we care? That is, how can a residual plot help us assess whether our model is wrong? Consider some examples. For our bad linear model of temperatures, notice that the curved pattern in the residuals captures the fact that our model doesn't cut through the trend in the data. Rather, at some places, mainly the beginning and the end of the year, so the beginning of the year and end of the year, it systematically overestimates the outcomes. And in the middle of the year, our model systematically underestimates the outcomes. In general, we don't need to even visualize the model or raw data itself. We can look at the residual plot alone. If there are any strong patterns in this plot, as we see here with this curved pattern, a very clear curved pattern, it's a sure sign that our model is wrong. But luckily, not all models are so bad. Recall that our quadratic model appears to cut through, thus accurately reflect the trend in the data. Across the entire model, the observed data points are balanced above and below the trend. Correspondingly, then, this model's residuals appear to be evenly and randomly balanced above and below 0 across this trend. In general, this is what a good residual plot looks like. If the residuals are balanced above and below 0, it's a sign that the data points are balanced above and below our model trend. That is, that our model is good. We'll get more experience looking at residual plots, but this is a good start and gives you a good sense of what an ideal residual plot looks like.